You were taught to sketch a curve by making a table of values. Pick some numbers, work out the heights, join the dots. On the curve we are about to draw, that method does not give a rough answer. It gives an answer that is wrong almost everywhere. Here is the function: x squared minus 4 all over x squared minus 1. Take the obvious numbers, minus 3 up to 3. 2 of them come back from the calculator as an error, so you leave a gap and carry on. The other 5 are honest. 5/8 at minus 3 and at 3, 0 at minus 2 and at 2, 4 at 0. Join them up and you get this. One smooth hill, 4 units tall, sitting on the axis at minus 2 and 2. And here is the curve those 5 points actually came from. Every one of the 5 points is on it. The curve drawn through them is not. The point the table calls the top of a hill is the bottom of a valley. And the 2 places it saw nothing at all are where the whole shape lives. The fix is not more points. Plot 100 and you still miss the 2 vertical lines because the curve is not defined on them. The fix is to stop plotting and start asking 4 questions in order. Where does it cross the axes? Where can it never go? Where does it turn? And what does it do far away? Question 1, and it is the cheap one. Where does the curve meet the axes? For the y-axis, put x equal to 0. The top is minus 4, the bottom is minus 1, and minus 4 over minus 1 is 4. So the curve passes through 0, 4, marked with confidence, not measured off a grid. For the x-axis you want the height to be 0, and a fraction is 0 exactly when its top is 0. The top is x squared minus 4, which is 0 when x squared is 4. So at 2 and at minus 2. One thing to check, the bottom must not be 0 in the same place. At 2 and minus 2 it is 3, safely not 0. If both vanished together you would not get 0. You would get a hole, and we will come back to that. So mark 3 points, minus 2 and 2 along the axis, 4 straight up from the origin. That is everything the table could have told you, and it took no arithmetic worth the name. It is also nowhere near enough. On this curve, what happens between those dots is the whole story. Question 2. Where can this curve never go? The one thing a fraction refuses to do is divide by 0. So find where the bottom is 0. X squared minus 1 is 0 when x squared is 1. At 1, and at minus 1, the curve simply does not exist. And check the top because it decides what kind of nothing that is. At 1, the top is minus 3, not 0, so this is a genuine blow-up. So rule 2 vertical dashed lines there. They are not part of the curve. They are walls it gets arbitrarily close to and never reaches. Draw them before you draw any curve at all. A sketch built around its walls comes out right. One that meets them by accident looks like that table. Now, which way does it go as it approaches a wall? You do not need values. You only need signs. Just to the right of 1, the top is about minus 3, so negative. The bottom is a very small positive. Negative over small positive is a large negative. So the curve dives towards minus infinity. Just to the left, the top is still negative. But the bottom is now a very small negative, and negative over negative is positive. So on that side it climbs to plus infinity. Same wall, opposite directions, decided by one sign. And the other wall comes free. X only ever appears squared, so the whole picture is a mirror image in the y-axis. Question 3. Where does the curve turn? A curve turns where its slope is 0, so we need the derivative. This is a fraction, so that is the quotient rule from lesson 9. Bottom times the derivative of the top, minus top times the derivative of the bottom, all over the bottom squared. The derivative of the top is 2x, so is the derivative of the bottom. Both are just the power rule. So the top of the answer is 2x, times x squared minus 1, take away 2x, times x squared minus 4. Expand and the cube terms cancel each other exactly. 6x is what survives. The slope is 6x, over x squared minus 1, all squared. 6x is 0 at x equal to 0, and nowhere else. so the whole curve has exactly one stationary point. Now look at the bottom, because it is doing something quietly enormous. It is a square, so it is positive everywhere. And a positive bottom cannot change the sign of anything, so the sign of the slope is simply the sign of x. So the one turning point is a minimum. Falling into it, rising out of it, and no second derivative needed to say so. And we already know how high it is. Question 1 found it, 4. Which is the sentence the table got exactly backwards? The largest number in it is the lowest point of the branch it sits on. And the outer branches never turn at all, rising the whole way on the right, falling the whole way on the left. Question 4, and it is the one that closes the sketch. What happens a long way out? You could put big numbers in. At x equal to 10, the height is 96/99, which is just under 1. But rather than trust a pattern, do one line of algebra. The top and the bottom differ by exactly 3, so write the top as the bottom, minus 3. Then the fraction splits, and the whole function is 1, minus 3 over x squared minus 1. As x gets large, 3 divided by something large goes to nothing, and the height goes to 1. So there is a horizontal asymptote at height 1. Rule it in, dashed like the others. And the same line answers the question almost nobody asks. Which side does it come in from? Outside the walls, x squared minus 1 is positive, so you subtract something positive from 1. The height is below 1, creeping up towards it. Between the walls it is negative, so you subtract a negative. The height is above 1. That is why the middle branch sits up at 4 and never comes down to that line. And it never actually reaches 1, because 3 divided by something is never nothing. Now put the 4 answers on one page, and the sketch draws itself. 2 walls and 1 floor. A middle branch down out of the left wall to a minimum at 0, 4, and back up the right one. A right-hand branch out of the bottom of the right wall, through 2, climbing towards 1. And its mirror image. And here is the real plot, laid on top. Nothing was fitted, nothing was measured. Every feature came from an answer. The recipe does not change from curve to curve. Intercepts, asymptotes, stationary points, end behavior, in that order because each answer narrows what the next can be. Run it on something that looks nothing like the first. X minus 1 over x plus 2. Intercepts, at x equal to 0 the height is minus 1/2, and the top is 0 at 1. Asymptotes, the bottom is 0 at minus 2, and the top is minus 3 there, so that is a real wall. Stationary points, the quotient rule gives 3 over x plus 2, all squared, and 3 is never 0. So this curve has no stationary points at all. That is a complete answer, not a failure. End behavior, same trick. The top is the bottom minus 3, so the height goes to 1. 1 wall, 1 floor, 2 branches, no turning points. Sketched in under a minute. 3 traps. The first is the hole. If the top and the bottom vanish in the same place, you do not get a wall. Take x squared minus 4 over x minus 2. Cancel, and it is just x plus 2 with 1 point missing at 2, 4. A hollow dot, not an asymptote. The second trap is believing a curve cannot cross a horizontal asymptote. It certainly can. X over x squared plus 1 goes to 0 far out in both directions, and passes straight through 0 on the way. Far away is a claim about far away. The third costs the most marks. Never substitute a number before you differentiate. Freeze the picture and there is no slope left in it. So where it crosses, where it cannot go, where it turns, what it does far away. Answer them in that order, and you will never need a table of values again.